Let me start. So the topic of my talk is this cusp singularities and the orientation distribution of asymmetrically pivoted system of hard disk on a lattice. Okay, so let us start. This work is done with Professor Deepak Dhar at IISc Pune, and some of it is published in Journal of StatMac last year, and some is in progress. Okay, so I'll just briefly talk about this work, the published work. So Professor Dhar actually has talked about it in I think in December here. So I'll just briefly talk about it, and then I'll present some new results. Okay. So the motivation of our work is actually the plastic crystal. It's less studied phase of matter in physics. So let me explain what is it. So for example, so we have seen this. We know this. There is a transition between crystal to liquid phase. It's a one-step transition. So crystal, I mean, by crystal, I mean that, for example, if you have the constituents, the center of mass of the constituent occupy a lattice site, and they can also rotate. So and the direction of, for example, it is ordered in certain direction, right? So that is a crystal. So here the translation symmetry as well as the rotational symmetry is broken. Okay, so you can have one-step transition. What can happen? There can be intervening phase between this crystal and liquid. So it is called liquid crystal, and it's much studied in physics. So here, as you know, so the translation symmetry is recovered, but rotational symmetry is rotation symmetry is still broken in the liquid crystal, and then you can get a liquid phase. But you can have another phase of matter in between. So intervening phase, it's called plastic crystals. So here the translation symmetry is still broken, but the orientation symmetry is there. So, okay, orientation order is not there. So it's orientation disordered. Okay. And you can have like different within, for example, the solution, you can have plastic crystal 1 where the translation, the lattice is different. Plastic crystal 2, it's changed to different crystal lattice. Okay, and then you can. So this actually is this plastic crystals are first studied in 1930s by chemists and starting with the work Timmermans. Okay. So here is a graph of plot of specific heat at constant pressure of cyclopentane as a function of temperature. So here, as you can see, the liquid phase here, and there are two plastic phase 1 and phase 2, and then there's a crystal phase. Okay. So why it's the name plastic? Actually, it's because of the flow properties. So for example, if you can see, so this phase 1 is plastic form, plastic crystal, and this form 2 is crystal phase. Okay. And Timmermans actually noticed that the pressure to go through a hole is very small as compared to the crystal. Okay, so that's why it's plastic. And it also noticed that this entropy of fusion is also very small. It's less than 5 calorie per degree per mole. For example, for first, I think up till here it's plastic crystal, and here they are not plastic. It's not so they don't go to plastic phase, plastic crystal phase. Okay. So what we have done in this work is to give a minimal model of this plastic crystals. Okay. So what's that? So one second. So this is, for example, you consider a hard rotor for any general shape, but they're identical, and pivot point is also identical of course, and they form a lattice. The pivots is in the lattice in d dimension, right? And it's a typical example of that. So it can be in any dimension or any regular lattice, right? So what we'll show, so we have like studied two examples. For example, this hard needles pivoted at one end on the square lattice, and this hard disk pivoted off center on a triangular lattice. Okay. So the partition function can be written like this. So where m is specifies the orientation, and we have normalized it in this way. Okay. And eta is something called overlap function. So it is 1 when the rotors at sites A and B overlap. It's 0 outside. Okay. So if they don't overlap, it's 0. And you can similarly define the entropy here because there is no energy. So it's defined by like this. And for if A is greater than A by L, so L is the, okay, so I forgot to mention, A is the lattice constant, and L is the distance between the pivot to the farthest distance from the pivot to the object, hard object. Okay. And it's greater than A by 2, greater than 2, then it can rotate freely, and the entropy is 0 because of this normalization, and it approaches minus infinity in the closed backing limit. Okay. So let us discuss this at most one overlap condition. So what is it? So there can exist some regime of, for example, this lattice constant where it can only interact with only one neighbor. Okay. So there, for example, mathematically what it means, for example, you take three distinct sites right? A I j k, and this product is 0. So this overlap function, this is 0, always 0, and it actually simplifies the partition function enormously. Okay? And for this hard needle pivoted one, and this regime is here, this. Okay? And for other models, you can find it out using simple geometrical arguments. So for example, now in AO regime, what we have shown is that this model becomes equivalent to dimer model. Okay, so this is the typical expansion term of this partition function, and this is nothing but it's a dimer because no two this bonds can overlap. So this is a typical term of the dimer model. Okay, so you can exactly write this equivalence is exact, and where z is the dimer activity. So this is given by this the double integral over it over eta, the overlap function, and this n of k is nothing but the number of ways of placing k over non-overlapping dimension on a lattice. Okay, so all well and good. So what can we extract, for example, from this mapping? So one thing is we can extract is probability distribution orientation of any site. Okay, so for example, it can be written as a contribution of two. So one is when there is no dimer. Okay, so it's a constant, it's independent of the orientation, and the another part is where there is a dimer there. Okay, and for example, A is nothing but the probability there is no dimer is 1 minus 2 rho z. Rho z is nothing but the density of the dimers, and this is nothing but this because of normalization they are connected, so they are not independent A and B. Okay? Yeah, so n is the total number of nearest neighbor, and rho z is the density of dimers. Okay, and f is you can exactly calculate using eta. So eta is also it's known from the model. So here is the overlap function on of hard needles on a square lattice. Yeah, so this is given by this, and here is the orientation distribution of the hard needles on a square lattice. So as you can see, the Monte Carlo, this dots are the Monte Carlo simulations, and these colored lines are the theoretical predictions. So they actually match quite well. So even though, for example, the density of the dimer model is not known exactly, but in the regime that we have seen, so there are various ways to find out the density of dimers. So there actually it matches to actually 3 orders of it's 3 degrees of accuracy. Okay? So this is the work that the published work. So this is the new result that I am going to show. So we have looked into, for example, this hard disk pivoted off center. So pivot are identical on each the disk, and it's off center, and now it's rotate. It can rotate provided that there is no overlap. Okay? So this car of unit size, lattice spacing is A, and pivots are a distance epsilon from the center. And here also this for this A greater than 2 times A 1 plus epsilon, it can rotate. Okay. And close packing limit is achieved when A is equal to 2. And thus we can, so if we have a mapping like A is equal to 2 plus epsilon x, we can do that, where x is in between 0 and 2. So we take this specific limit epsilon tends to 0. So here actually it specifies a lot without like the physics remains even if take this limit. Okay, so when we take this limit, the hardcore constraint actually for example to first order of magnitude or in epsilon, there is no epsilon. So the correction will be quadratic order. We ignore that, and the hardcore constraint actually reduces to this, and this model actually becomes equivalent to system of planar spins whose Hamiltonian can be written like this. Okay, so where j tends to infinity, and this is model, right? And where these are the neighbors. Okay, so here also you can write the overlap function. It's all known. Now comes the probability distribution. What happens to that? So here also, so you can write the probability distribution as a sum of 6, actually 7, and where PR is the contribution corresponding to exactly R overlaps. Okay, of the disk at the origin with its neighbor. So we are just finding out the probability distribution at the origin, the disk at the origin, right? So here is the regime. For example, x greater than 2, there is no overlap, and in this this is AO condition where exactly one overlap can happen, and there these are the whole other regime where you can have 2, 3, 4, 5, 6, at most 6 overlap can happen in this model, right? So AO regime, this all the terms greater than 1 vanish, and you can write again like this form, and Fi we know. Here also this is given by this quantity. Okay, and other Fi's can also be like found from Fi's F1 using symmetries of the triangular lattice. Okay, So here also you can, for example, this when there is AO condition is there, so this are theoretical prediction and the Monte Carlo simulation matches. And apart from that, you can see there is a cusp singularities here. Okay, and we can also theoretically like say that this position is also known exactly, and there are square root singularities. And the position of, for example, other singularities, so there are 11, 12 of them, and the position also is, the position is given by this. So we know exactly where are these. Okay. So what happens, the question is what happens beyond AO? So beyond AO, this mapping is not there. So it actually maps to a mixture of like k-mers. Okay? And in order to obtain the density of different k-mers, it's very difficult. So we can't like write on the exact probability distribution. What we can do is we can actually, for this model, we can predict the position of singularity and the nature of the singularity. That is robust. So that is actually is what it's in the AO phase. Okay, so for example, here it starts to break down. So here it's like the last point where the AO condition is hold. For example, here, so these position of cusps are exactly known to 3 digits of accuracy. And again here, and these singularities actually move, we can actually find out where the singularities are. Okay. So up till here we can do that, all this thing, right? So here, as you can see, in all this, there is no symmetry breaking. Up till here, there is no symmetry breaking. Below x, what happened, I was doing this Monte Carlo simulation. Below, for example, 0.9, the system doesn't equilibrate. It's taking a very long time to equilibrate. So between 0.5 to this 0.5 and 1, then system is not equilibrating. Just below, for example, 0.5, it equilibrates, and there is a symmetry breaking transition, as you can see here. So here, just below, for example, x is equal to 0.45, so there is symmetry breaking transition, and it is peaked around pi by 6. Okay, so there is disordered phase, there is this symmetry breaking phase, this we can say it's crystal phase, and then there is in between there is some phase. So there is strong evidence, I think we have numerical, that is a Kosterlitz-Thouless phase. So yeah, so these are new results, these are not published, so we are still, it's still a work in progress. Okay, thank you.
Now we are open for questions. Okay, no questions. Thanks to speaker.
Thank you, Samiksha. Okay, so fine. It was great fun. At least, I mean, I think all of us enjoyed being together and chatting, discussing science. So we really hope to see you again next year and have safe flights and enjoy your evening.